Okay, good morning, ladies and gentlemen. Good afternoon, good evening, depending on where you are and the time you're watching this. Welcome to our thermodynamics laboratory. So today we're going to demonstrate a fundamental principle in thermodynamics, specifically in heat engines. This principle states, in a nutshell, that the efficiency or the Carnot efficiency, the maximum obtainable efficiency of a heat engine depends primarily on the temperature difference between the hot reservoir and the cold reservoir. Remember, a heat engine is a system, a device that receives heat from a high temperature reservoir, does work with the heat, and then rejects residual heat to a low temperature or a cold reservoir. To improve the efficiency, you either increase the temperature of the hot reservoir or you reduce the temperature of the cold reservoir, or you do both. That is, increase the temperature of the high temperature reservoir and reduce the temperature of the low temperature reservoir. So in this experiment, we're going to prove that principle to be true. And to do that, we have a very simple experimental setup here. Here we have our heat source, which is a heat gun with adjustable temperature. So we can vary the temperature. If we vary the temperature here, then we are essentially varying the temperature of the high temperature reservoir, as we will see shortly. Now, this is our heat engine here. It's a Stirling engine mounted on a retort stand. Now, what happens here is that this side of the engine is a hot side. The heat from the high temperature reservoir is sent to this side of the system, and then it leads to expansion of the gas contained within. The expansion of the gas leads to movement of a piston within, and that in turn translates into a rotational motion that moves the wheel. So work is done by the heat from the high temperature reservoir, which is the heat gun now, and then the low temperature reservoir is essentially the ambient, and this is the cold side. So this other side of the heat engine rejects residual heat to the ambient. So now let's demonstrate how the different temperatures will yield different efficiencies. And remember, efficiency is the ratio of the work done to the heat supply. And work done is force times distance, or torque times angular speed. And since we are operating on a low load situation, we are operating essentially at constant torque, no load torque. So a change in efficiency will directly manifest in a change in wheel speed. So when the efficiency increases for the same torque condition, the speed will increase. So let's demonstrate how that happens. Now, to start our experiment, we set the temperature at 100 degrees Celsius. So this is the temperature of the high temperature reservoir or the hot reservoir. Is set at 100 degrees Celsius, and we'll place it appropriately so that it delivers heat to the heat engine. And then when we wait for a while to ensure proper heat transfer has taken place between the hot reservoir and the gas within, or the air within the heat engine, Stirling engine, then we can give the heat engine a bit of a push so it can start rotating in response to the heat input. So as we can see, work is being done. So heat from the high temperature reservoir is being converted to work, mechanical motion of the wheel. And then residual heat is rejected from the low temperature reservoir. So you can observe the speed of the wheel at a hot temperature of 100 degrees Celsius and a cold temperature of normal ambient conditions. Now, as I said earlier, one of the ways to increase the efficiency will be to reduce the temperature on the cold side of the low temperature reservoir. And to do that, I have with me here a refrigerant spray. So I'm going to spray the refrigerant. Now, when we say refrigerant is a coolant. That's what you use in your refrigerator to essentially withdraw heat from within the evaporator and so cause the cooling effect. So we're going to induce a cooling effect on the cold side and so reduce the temperature so that, and then observe what happens to the speed of the wheel. So I'm now spraying. Can you observe the increase, the dramatic increase in speed of the wheel? The speed of the wheel increased tremendously. So that demonstrates the validity of the principle. By reducing the speed, the temperature of the cold reservoir, we are increasing the temperature difference between the hot reservoir and the cold reservoir. And as such, we're increasing the Carnot efficiency of the heat engine and as so and therefore the actual efficiency. And a change in efficiency manifests in a change in speed for constant torque. So you see that the efficiency and hence the speed of the engine has increased by reducing the temperature on, the temperature off the cold reservoir or the low temperature reservoir. So the next thing we're going to do is to increase the temperature of the hot reservoir. So currently it's at 100 degrees Celsius. So I'll set it to let's say 130 degrees Celsius. I've set it to 130 degrees Celsius. And let's see what happens to the speed of the wheel. Again, the wheel speed has increased as expected by the principle, or as expected based on the principle. So you see that the principle has been demonstrated the speed has increased tremendously. Okay, so we've demonstrated the principle. I hope you enjoyed it. If you have any questions, please write. We will respond. So thanks for watching. Thanks for listening. Until we come your way again, this is Jay signing off.